I wanted to talk about is quantum key distribution. So quantum key distribution is a cryptographic protocol. We already talked about cryptography a little last week. But last week I was talking about how quantum computers are bad for cryptography. Well, bad for making code, so they can break RSA, one of the commonly used crypto systems. But today I'm going to talk about how quantum information can help create more secure cryptographic systems. So recall that the situation in cryptography is we have Alice trying to send a message to Bob. There's an eavesdropper, Eve. And the advantage that Alice and Bob have over Eve that lets them potentially get away with this is that they have some secret key that they've set up ahead of time. In the case of the public key system, Bob had the decryption key and Alice had the encryption key. But remember, I also mentioned a symmetric, the strategy of symmetric crypto systems. Where Alice and Bob share the same key. This is called the private key. And so the idea here is that this key K is used for both encryption and decryption. And public key crypto systems have a lot of advantages. They're more flexible about how you deal with the encryption key. But private key crypto systems have advantages too, and one of which is that they can be much more secure. So for instance, while public key, it's quite common that both public key and private key crypto systems depend on some bound on Eve's computational power. Private key crypto systems tend to be harder problems. So for instance, whereas RSA can be broken by a quantum computer, the most common private key symmetric crypto systems, we don't know how to do that. You can speed up the attack on them using something like Grover's algorithm, but we don't know how to completely break them. Now, there are other public key classical crypto systems that we don't know how to break on a quantum computer, but it's still the case that in order to have a public key system, you need some kind of additional structure beyond what you need for a private key system. And that additional structure creates extra avenues for attack. Moreover, there are symmetric private key crypto systems that don't depend on a computational bound on Eve at all. And in particular, there's something called the one-time pad. So in the one-time pad, the key K is going to be n random bits. Just totally random, and that's the bit string K. And in particular, these random bits are unknown to Eve. And then to encrypt, so Alice has the message M, which is n bits long. The same n, that's important. And the ciphertext is E, which is M plus K, bitwise XOR of M and K. So in other words, if the first key bit is 0, then the first message bit, the first ciphertext bit is the same as the first message bit. If the second key bit is 1, then the second ciphertext bit is the opposite of the second message bit. OK? And while naively you might say, oh, well, that's really dumb because half the key bits are 0, which means the message bits are the same as the ciphertext bits. And so Eve is getting half of the message bits. The reality is that he doesn't know which ones those are, right? And if you think about it, this k is uniformly random. It could be anything, which means that from Eve's point of view, given a specific ciphertext E that she sees, well, M could be anything as well, right? For any value of E and K, there's a consistent M, right? And in particular, for any M, there's a K that's consistent with E. That's maybe more important. Okay? So from E's point of view, the message M is uniformly random. She has no idea what the message is. I mean, she might have some previous idea what the message was, but she doesn't gain any extra information about it. And so that's why this is information theoretically secure. And then the decryption, Bob has the key K, so it's really straightforward. The decryption, you decrypt to E plus K, which is just equal to M. Right? So you XOR with K again, and you get exactly back to where you started. OK? So this crypto system is information theoretically secure. It does not depend on any computational assumptions by Eve. If Eve really can't peek inside Alice and Bob's computers, and she doesn't know anything about the key, she really has no information, gains no information about the message. OK? So this is a really powerful crypto system, and it is used in the real world. But it has some big disadvantages. Most notably, the key here is n random bits when the message is n bits long. And if you make it any shorter than that, or you reuse this key in 2 different messages, then you no longer have information theoretic security. And in fact, historically, there was a case where during the Cold War, the Soviet Union accidentally had code books where they printed the same page twice. And so they ended up using the same keys twice. And the US was able to break a number of Soviet messages to their spies in the US using this extra information that they had. Okay? So it's a real danger that if you're not careful about how you use this key, that it's not secure anymore. And so you need this long random key, and you need to keep using them up. That's why it's called the one-time pad. Keep using them up and having more and more bits used up as you send more and more messages. And so that means that you have to put a lot of effort into establishing the shared secret key, because remember, Alice and Bob have to both know what it is, and Eve has to not know what it is, right? So that's a pretty big thing, and you have to keep it, of course, secure in the meantime. If Alice and Bob got together to share this secret key, they have to keep it away from Eve for however many months or years they're going to be using to communicate secretly. Okay, so that's a big drawback, and it's a reason why it's not more widely used. Yeah, and so of course the other disadvantage of any symmetric key crypto system that you don't have with the public key crypto system is you can't communicate with somebody that you don't have a prior connection with, right? So Alice and Bob had to share this secret key K, but if they never met before, how are they going to get that secret key K, right? I mean, they could send a messenger between them, and they have to trust the messenger. And they both have to know who the messenger is, so they know that they're getting to the right person, and so on and so forth. So there's a big overhead involved in that as well. OK? So this is one reason why, say, on the web, public key crypto systems are much more widely used. Because if you go to a website, you can find its public key without necessarily having to have been to that website before. Or worse, having to been to the company, physically been to the company where that controls that website. OK? So quantum key distribution is basically a method of setting up this secret key in a way that is much more flexible and more secure. That can be, in particular, can be done remotely. It still has some drawbacks. It's not quite as powerful as public key crypto system. And of course, another drawback is you need quantum communications. but it's still a lot more flexible than what you get with classical private key crypto system. OK, so let's see. I guess I'd probably start a new board here. OK, and in particular, I'm going to talk about the BB84 protocol. So the BB is Bennett and Broussard, and 84 is because it was published sort of in 1984. So this is the kind of the standard, most common QKD protocol, but there's many, many others. And so here's the way it works. So the first thing is that Alice is going to generate a bunch of random numbers. So we're going to say there's big N random bit pairs. So it's actually 2 times big N random numbers, random bits, AI and RI. And then, so each of these pairs is supposed to specify a quantum state. So how does it do that? Well, it does so according to this table. So AI is the basis, and RI is the state in the basis. So if AI is 0, we're going to do the Z basis. So we send the state 0 or 1, depending on what RI is. And if AI is 1, we're going to do the X basis, the plus-minus basis. And so if RI is 0, we send the plus state. And if RI is 1, we send the minus state. OK? And so Alice then is going to create these states. And sends them to Bob. On the quantum channel. OK? So far, pretty straightforward. So maybe at this point, I should stop and talk about what assumptions I am making here. So I'm making the assumption that Alice and Bob share a quantum communications channel, obviously, because we're going to want to send qubits from Alice to Bob, like here. And Alice and Bob are also going to share some classical communications channels going in both directions. So they can talk to each other over the phone. And the assumption specifically the assumption is that the quantum channel from Alice to Bob is completely insecure. In the sense that Eve has total control over it. OK? And the classical channels go in both directions. And Eve can read them but not change them. OK, and I'll get back to that assumption later. Of course, it doesn't really make sense to talk about a quantum channel that you can read but not change, because measuring a quantum state is going to collapse it. It's going to change the state. So we're just going to give Eve complete control over the channel between Alice and Bob. She can, take the qubits away. She can alter them. She can measure them. She can do whatever she wants. But then Alice and Bob can also talk classically. Eve can listen into that, because if you didn't let her listen in, you wouldn't need a quantum channel to have. You'd already have private. You already have a secure encryption system. But we're not going to let her change them. And that's, like I said, we'll get back to that assumption later. OK, so Alice sends these qubits to Bob. And then Eve does whatever she wants to them. Bob receives them. Whoops. And then Bob is going to choose his own set of random bits. But he's just going to choose the bases. So he's not going to choose pairs of bits. He's just going to choose big N single bits. And those are going to specify bases to measure in. So he measures qubit I in basis BI. OK? And then when he does so, he gets a result, which I'm going to call SI. OK. So now the next thing that happens is they start to use, they're done with the quantum part of this protocol. But there's still a bunch of classical steps. And so in particular, the next step is Alice and Bob announce their bases. OK. But yeah, let's do it over the classical channel. But they don't announce the other bits, Ri and Si. And so the purpose of doing this is so that they can compare which basis they used. So if Alice and Bob use the same basis, then they keep the bit. And if they have different bases, then they discard that bit. So just some terminology here. So the bits Ri and Si that they keep are called the raw key. OK? So let's think about this for a minute. So why are we doing this? Well, if Alice and Bob use the same basis, then Ri and Si should agree, right? Because if Alice sent this state and Bob measures in that same basis, then in the absence of any kind of errors, Bob will just get the same result as Alice. OK? On the other hand, if Alice sent it in the X basis and Bob measured in the Z basis, or vice versa, well, if Bob measures the plus state or the minus state, either way, he'll get 0 and 1 with equal probability. And so his bit Si will be random. It'll be uncorrelated with Ri. OK? Again, in the absence of anything else going on. So that's why they want to throw away these cases where AI and BI are not equal, because they're not really getting anything useful out of that. In these cases, they're supposed to be the same. But now let's see what happens if there's an eavesdropper involved. Okay? Eve, remember, has to intervene at this step, after step 2. This is before Alice and Bob are announcing AI and BI. So Eve doesn't know what basis it is either. And so Eve, well, she might try to do some measurement, for instance, to try to figure out what the bit Ri is. So for instance, if Alice sent in the z basis, AI was 0, and Eve measures in the z basis, then she'll learn what Alice's bit is. And if Bob also measures in the z basis, Alice and Bob will keep that bit, and then Eve knows 1 bit of the raw key. Okay? But the problem is, what if the basis actually was the x basis, and Eve measures in the z basis? Now, first of all, the bit she's getting is random. It's not telling her anything about Ri. But moreover, she has to send the state on to Bob, right? And a natural thing for her to do is to measure and then send on to Bob the state that she got. So if she measures in the z basis and gets a 0, she's going to send Bob the state 0. Okay? But Bob, if Alice and Bob are keeping this bit, is also measuring in the x basis. And if he gets the state 0, well, that's equally likely to result in a plus state or minus state. Right? And so while Alice might have sent the state plus, half the time Bob will get the state minus. And Ri and Si will not agree. Okay? So even if there's no other source of error in the system, Eve's eavesdropping is introducing errors, cases where Ri and Si will not agree. Okay? And so that's the kind of the key step in QKD is to understand that when Eve tries to eavesdrop, she can only do so by introducing errors. Any kind of information gain she might get about the state creates a disturbance that Alice and Bob can detect. Yeah, so of course, what I told you was just one potential eavesdropping strategy. There's many others. But it turns out that this is just a universal property. Either Eve can do something that's not very useful for her. She doesn't learn very much, but that doesn't disturb the state very much. Or she can try to gain some information, but in doing so, she's going to disturb the state and create errors. OK, so how do we find out? So Alice and Bob, at this point, haven't said anything about Ri and Si, so their bit strings might disagree, but they don't know it yet. So they have to do something to compare to find it out. Of course, they don't want to announce all of the bits, because then, even if there wasn't an eavesdropper before, even if the eavesdropper didn't do anything before, the eavesdropper would then know their whole key. But they can announce part of it. So what they're going to do is they're going to choose a random subset. Which you might, the size is not, it could be really anything, but let's say half the raw key. And announce Ri and Si over the classical channel. So they compare these and calculate the error rate. So if the error rate is, so the problem is, if all their system were completely perfect, then the only source of error would be an eavesdropper. And so you could say, well, if there's any errors at all, let's throw this out and try try again some other time. But of course, in the real system, there will be errors. Hopefully not too many, but there'll be some. And so they don't want to throw it out, even if the error rate is small but non-zero. They want to be able to keep it. And so we're going to need to do some steps to take account of that. But if the error rate is too high, then it's just kind of hopeless. They won't be able to make the QKD work at all. And so if they're too high, they discard everything and end the protocol. Abort. OK? Otherwise, they continue on to these other steps. So suppose they do find that the error rate is low, but maybe non-zero. So the part of the key that they haven't announced is also going to have errors in it, most likely. And they would like to have this secret key that's the same, so that the decryption works in the one-time pad. And that means that they have to get rid of those errors. So they're going to do some error correction. So they announce parodies of subsets of bits corresponding to parity checks of a classical error correcting code. Yeah, and so using this information, they correct errors in their remaining bits. And the thing is that, I mean, I guess I didn't say it explicitly, but of course, when they announce half their bits in the step 5, in order to compare them, they're not going to use those bits again, right? Because Eve knows them. They're not worth anything. And these parodies, they're not explicitly the values of individual bits, but they are some information about their bit strings. And so to make up for that, they should discard some bits as well. And discarding one bit per parity is sufficient, right? Because the parity is saying whether this set of bits is even or odd. And if you throw one of those bits away and it's random, then the remaining one could be even or odd. So you've kind of eliminated that information. OK. But the problem is that at step 5, since we didn't throw it away, actually it didn't even matter about this. But the error rate is non-zero. We didn't throw it away even by detecting a single error. But even suppose there were no errors detected here, it's still possible that Eve got lucky and she measured a few bits, either without creating errors, or she created errors, but they're not in the set that we tested, right? So it's possible that Eve has a few bits of information, right? And when the error rate is non-zero, it could be some constant fraction. Small fraction, but still a constant fraction of all the bits. Of course, some of those errors are probably due to noise and real noise in the system. But maybe the noise is not as high as you thought it was. Right? Maybe Eve is doing something to improve your optical fiber just so that she can eavesdrop some more. And so we're going to assume the possibility that all the errors in the system really were caused by Eve. And so that means that she could have some information about some of the bits, and we have to get rid of that somehow. So they do something called privacy amplification. So again, they're going to choose random subsets. And they're going to compute the parity. So these parities they're not announcing. And they use them as the final key. OK? And then everything that's left over, they discard. OK? So what's the intuition here? Well, the intuition is, so after this step, Alice and Bob have corrected their errors, so their remaining bit strings are all the same. So when they take the parity of some subset, they should get the same result, right? So they don't need to do any comparison, public comparison, to check that that's working. And they don't want to because those parities are going to be the key. So why is this more secure against Eve than this thing? So again, think of the situation where we have some long list of random bits here, and Eve knows some of them. Well, when we take the parity of some subset, Eve has to know all of those bits, or at least know a lot about all of those bits, in order to have a good guess on the value of the parity. Again, if Eve is missing just one of those bits, then the parity could be, I mean, that one bit could switch the parity from even to odd, or vice versa. OK? And so if she knows nothing about any of the bits in the parity, then she's out of luck. And so that's what they're doing here. They're kind of squeezing out Eve's information. And so whereas they did have an advantage over Eve, Alice and Bob knew all the bits, and Eve only knew some of them, or knew some partial information about them. After this, Eve knows extremely little. Depending on how much privacy amplification, you can make it, on average, a small fraction of a bit. So much less than 1 bit of information. OK? You can make it exponentially small, in fact. OK, so the upshot is that Eve has to make a choice when she makes her attack. So, and based on that choice, a strategy of how she's going to attack the system, Alice and Bob will see one of two things. So either Alice and Bob reject the key with high probability, And high probability in this case means 1 minus 2 to the minus s, where s is some security parameter. So really, really almost certain that they'll reject the key by catching Eve. Or Eve has very little information. And again, this means an exponentially small amount. So it's like 2 to the minus s bits about Alice and Bob's key. OK? OK, so obviously, I have not given you a full security proof of this. The security proof is fairly involved, because when you think about what Eve can do, she has a huge range of options, right? Not only can she do the kind of simple intercept resend strategy I said, where she measures a state and then sends on the result based on what she got, but she can do weak measurements on these states. She can interact it with a quantum ancilla that she keeps behind, and then measures later after Alice and Bob have announced their bases. She can do some collective thing where she entangles all of the qubits that Alice is sending to Bob, and does some joint measurement, or again delays that measurement by keeping some quantum register around. So she really has very many options for what to do. But you can prove that no matter what she does, this holds true, or some similar sounding condition. OK? So there are questions about, yeah?
So what is the exponent in 2?
2 to the minus s. So s is some security parameter. You set it at when you do this protocol. Yeah?
Is there potentially a way to distinguish between an eavesdropper and noise in the system? To distinguish your source of error?
No. And the reason for that is that we're making very few assumptions about Eve, about her capabilities and what she knows and what she can do. And so Eve potentially knows what the normal noise in the system is. So we should imagine 2 situations, OK? So in one situation, there's no eavesdropper. We're just running it. There's some kind of normal, natural noise in the system. And the other, Eve has replaced everything with really, really high-quality components that she controls. OK? And so she can do whatever she wants, and there's no other noise in the system. And the thing is that Eve might know everything about the kind of noise that you see in the first case. And she wants to disguise the fact that she's attacking. So she's going to make her attack look like the noise that you would see normally in the system. And there's kind of no way to distinguish if Eve is good at her job.
I have another question, and this might be really sneaky. Why do we assume that Eve doesn't know how we choose our bases?
Yeah. So this is getting back. So sometimes you'll see that people talking about QKD as unconditional security. But that's not really true. When I said it, I said information theoretic security. And so there is some security condition here. And the security condition, the main security condition, is that Alice and Bob have private labs. Eve cannot look inside them. They can do what they want, and they can do it relatively perfectly. When you start to have imperfections in Alice and Bob's devices, then you can start to open up security holes. And I think there's one in the tutorial on Friday that you'll be examining. But yeah, so the assumption is that Alice and Bob, they have random number generators in their labs. Eve cannot look in them. And so they can safely generate those random numbers that Eve knows nothing about. But actually, generating random numbers is a fairly hard task. So that's also a little bit unsecure. So there's nowadays there's actually some related protocols to QKD where you can use quantum mechanics to securely generate random numbers. There's still kind of a chicken and egg problem in that you need a few random numbers to start with in order to generate more. But that's a whole other story. Any other questions? OK, so I guess one thing I didn't tell you is, or apparently write down, so in step 5, I said they should abort if the error rate is too high. So what's too high? So that's something that has to come out of your security proof, right? Your security proof says that if the error rate is below this value, then privacy amplification will squeeze out. Then, for a given value, Eve has a certain amount of information, potentially. And then the security proof will tell you that if that information is below some amount, then privacy amplification will squeeze out that remaining information, and you'll get the security condition that you wanted. Okay? But if it's too high, then privacy amplification might not work. At a minimum, how many parities can you keep? How many bits of real key can you keep? That's, again, something that has to come out of the security proof to say how much it's safe to keep. If you try to keep too many, the more parities you take, the more likely it is that Eve luckily gets one set that she knows everything about, or a lot about. And so it might not work then. So the kind of the trade-off of how much privacy amplification you have to do versus what the error rate is, again, that's something that comes out of the security proof. And if the error rate is too high, then it may be you can't do privacy amplification at all. Okay? Your key rate generation will go to 0. And for BB84, it depends a little bit, but that happens kind of at the 15 to 20% error rates. So it's a pretty high error rate that you can tolerate and still have some key. But of course, at the upper end, the rate of key that you can generate there gets to be quite small. So you don't want to have to do that. Yeah, OK. So questions about that? Yeah.
So on step 6, if there's multiple errors, then in the string that you're checking the parity of, then
Right.
Alice and Bob will think that they have a key at the end of the day, but it's going to be incorrect. Right?
Yeah. So again, the amount of error correction you need to do is going to depend on the error rate, right? If there's a high error rate, they need to measure lots of parities and announce lots of parities in order to be able to correct that. If this error rate is low, they don't need to do that. And the key here is that in step 5, they're taking a random sample of bits and comparing to figure out the error rate. So it's very likely that the error rate that they calculate in step 5 represents the actual true error rate on the remaining 50% of the bits. Okay? So they do have a pretty good idea what that error rate actually is. Now, it could be, of course, that Eve could be introducing highly correlated errors, but actually that all still works the same way.
But there is still a chance that they think that they've succeeded and they start trying to use it.
Yeah, that's true too. So this is not exactly the security condition, but that's another aspect of this, that there's also an exponentially small chance that their keys don't agree. That's another kind of failure of the protocol. But again, as part of the security proof, you can show that that's very unlikely. Yeah. OK. Any more questions? Yeah.
Kind of a silly idea. The quantum teleportation is kind of a way of sending information, right? Could that be used?
Yes. I'll get to that in a little bit. Yeah, so let's. Here's one thing I can say right now. So Alice is sending her qubits to Bob over the quantum channel. And you might say, well, that's a natural candidate to be replaced by quantum teleportation. So instead of doing that, maybe Alice and Bob can create EPR pairs that don't depend on the qubit that Alice is trying to send, and then measure those. But of course, the problem is you had to create those EPR pairs. And so there's various ways you can imagine doing this, but the thing that's most analogous to QKD is you send one qubit over the channel, and then Eve has a chance to attack it, and they no longer have EPR pairs. And it turns, I mean, there's a kind of equivalent protocol. There's a slightly different protocol called Lecture11, which is very similar but not quite the same. That's the whole protocol. Alice and Bob generate EPR pairs, and then they measure them on their sides. And that does have some concrete advantages. You don't actually have to teleport, because really all they're trying to do at the end of the day is get classical information that they agree on and that Eve doesn't know. But yeah. Anything else? OK. So now let me get back to this assumption that the classical channel cannot be changed. OK. So suppose we relax that assumption. What could happen? So in particular, if she could change the classical channel, she could impersonate Alice and Bob to each other. And so she could do something like this. So Alice is going to be over here, Bob is going to be over here, and Eve is going to be something called the man in the middle. It's the man in the middle attack. OK? And so Alice is going to be sending qubits to Bob, but Eve intercepts them. OK? And Eve is going to do everything that Bob would have done. So she measures in a random basis. She records those values, and then she announces the bases to Alice, pretending to be Bob. And she can also change the classical channel so she can interrupt Alice's classical messages to Bob. And basically, Eve just does this whole QKD protocol pretending to be Bob. OK? And so at the end of the day, Alice thinks she's generated a secret key with Bob, but she actually generated a secret key with Eve. OK? So Alice and Eve have some key K. And meanwhile, while she's doing that, Eve is sending qubits to Bob, pretending to be Alice. And then Bob goes ahead and does his half of the protocol, and he announces his bits. Eve intercepts announces the bases. Eve intercepts that. Eve sends back her choice of bases, pretending to be Alice. And Eve and Bob go through the whole QKD protocol, where Eve is pretending to be Alice. OK? And at the end of that, Bob thinks he's generated a secret key with Alice, but actually he's generated one with Eve. So they have some shared key K prime. OK? Now, of course, if Alice tries to send a secret message to Bob, then she'll encrypt it with K. And if Bob got that, he wouldn't be able to decrypt it. And then maybe they'd realize that something was wrong. Though, of course, by then it would be too late, because Eve has been listening in, and she could decrypt the message, so she would learn it. But moreover, it's worse than that, because remember, Eve can change the classical channels. So what she can do is she can intercept Alice's message, decrypt it, read it, and then re-encrypt it using the key K prime and send it on to Bob. OK? So Alice and Bob can communicate just the way they could before, and they have no idea that Eve is reading all their messages. OK? So this is clearly a very powerful attack, and that's why we don't allow this to happen. Right. So how do we prevent that? Right. Obviously, that's a seemingly a big assumption. So this is called. So there's classical protocols to do this. This is called an authentication protocol. And the idea is that Alice can so in there are secret key protocols that will do this with information theoretic security. So what does that mean? So it means that Alice and Bob will share some secret key, just like with the one-time pad. And Alice will use that secret key to generate a small additional set of bits to append to her messages. And that extra thing will prove that the message really came from Alice. Okay? And so Eve won't be able to send this K prime to Bob, right? Or to send the set of bases to Bob. Because to do that, she'd have to send Alice's actual bases. Right? Because she can no longer change Alice's messages without being detected. And so this whole thing breaks down. And with this type of situation, you get back to the case where the classical messages can be read by Eve but not changed, and you have the whole security proof goes through. Now, this might seem really dumb. I mean, of course, you're using this secret key, and then you use it up to create the authenticated channels, and then you're just going to generate more via QKD. So how are you winning? And the answer is the amount of secret key you need to do authentication is much, much less than the amount you need to do encryption. Okay? So if you have a small amount of secret key to start with, then you can generate more secret key. So that's in the situation where you really want full information theoretic security, that's the advantage of QKD, is it eliminates the need to have really, really long private keys. You can have short private keys, start from there, and then build up more as you need it to send messages. Now, if you're willing to step back a little bit on your security condition, you have many more options. So for instance, one option is if there's some trusted third party in the middle. And so Alice and Bob maybe have never communicated directly before, but they both have talked to somebody else that they do trust. Okay? But they trust them only a certain amount. Okay? They trust this person enough to relay their messages accurately. So they have shared private key with this third party. And so they can authenticate messages to the third party and have the third party authenticate them to Bob. But they don't trust the third party enough to read their real secrets. Okay, so they don't want to just send their encrypted messages to the third party and have him re-encrypt to Bob. Okay, so in that case, again, this private key, this quantum key distribution protocol will give them what they want, because they can use that trusted third party to authenticate messages, but they then can establish a secret key that even the third party doesn't know about. And so then one additional option is I told you about public key encryption protocols, but there's kind of a related protocol called the digital signature protocol. And in the digital signature protocol, you have a public key, you have a private key that's used to authenticate messages, and a public key that's used to verify them. So there's this asymmetry. And so the public key can be given out to anyone, including Eve. And then once you've done that, Alice can send a message to Bob, and Bob can verify that it really came from Alice. Now, of course, it's a public key system, so it depends on some computational assumption. So you're really no longer in the realm of information theoretic security. But it's still more powerful than what you could get from public key encryption normally. Why is that? Well, normally, Alice encrypts using RSA or something like that, public key protocol, and sends it out. Eve can copy down the ciphertext. And then she can take her time to break that system, right? So if she has maybe not a quantum computer, but some very powerful classical supercomputer, then she can put lots and lots of computational power And then eventually, maybe she can break this system and read what the message is. But in order to make that attack work with the public key, if Alice and Bob are using public key crypto system to communicate securely, then Eve will have to break those messages, break the public key system in real time, right, while Alice and Bob are doing the QKD protocol. So she has a much more limited time scale in which to work on this problem. And so it's quite reasonable that if you have such a crypto system, that Eve would not be able to do it in that time. And then once that happens, that means that the messages Bob received had to be the ones that Alice was actually sending. And therefore, the QKD protocol works, and the key that they get at the end actually is information theoretically secure. Okay, if Eve can't break it before the protocol ends. Does that make sense? OK, and maybe one more comment. So really what you see quantum key distribution is doing is it's turning an authenticated channel in any of a number of ways into a secure channel to distribute key. And if you think about it, this is actually what public key cryptography does as well. Because Bob had to get this public key, or sorry, I guess the way I set it up, Alice had to get the public encryption key from Bob at some point, right? And how did that happen? Well, it had to happen over an authenticated channel. Because otherwise, Alice could have gotten Eve's public encryption key. And Eve could do a man-in-the-middle attack against a public key system just as well, if you really have no kind of authentication. Now, public key crypto systems are still more flexible. There's still more options with them than QKD. But basically, they accomplish something kind of similar, which is turning this authenticated channel into a secure encryption channel. OK? OK. So then one more point. So QKD is actually a lot easier to do than a quantum computer in the following sense. Well, experimentally, you just need to generate single qubits, send them over, say, some optical fiber or through air, and be received by Bob, who makes a measurement. OK? And it even tolerates a non-zero error rate, and you can still have security. And so QKD experiments has been done for a long, long time. There are commercial QKD devices out there that you can buy if you have enough money. The problem is that this protocol, as I've described it, is definitely going to have some limit of how long a distance you can do it over. Why is that? Well, the longer the distance, the more likely you are to have errors along the way. The dominant thing is the loss of photons, which is not too severe by itself, because a photon that doesn't get from Alice to Bob just doesn't count in the key, so it doesn't really matter if Eve learns it or not. But it can combine with other things, other imperfections in the system, to make a real security loophole. And I think that really is what the tutorial is about. So there is a limit to how far you can do QKD over in the way that I've said, which is on the order of 100 or 200 kilometers. I guess it's maybe a little more, 200 to 300. There are some extra tricks you can do to increase the distance. So that's a big limitation. So what can you do to go beyond that? So one possibility is to have trusted way stations along the way. And this is not like the trusted third parties from before, where you partially trust them. You have to really completely trust them, because you're establishing secret key with those way stations. And then they have to re-encrypt and send the message on to the next stop. OK? And so if Eve breaks into one of those, the computer is in one of those way stations, she can learn the message. Now, you can ameliorate that somewhat by having kind of multiple different paths and taking the XOR of keys from different locations. But it still is, creates a potential vulnerability if you don't have a wide network of places that you can really trust. So another strategy, a kind of related one that people have talked about and actually started to implement, is to put up satellites. And so the basic version is simple, where where the satellite is trusted. It's up in space. It's probably hard to get to. So Alice establishes her key with the satellite. The satellite travels around the world. And then Bob is now below it. And so he establishes a secret key with the satellite. And you can communicate back and forth that way. So again, it has the same problem that if somebody does manage to hack the satellite, then you're out of luck. But it's in some sense an improvement over having to have physical buildings that you're protecting scattered around the world. And in fact, people have done basically this. China at least has a quantum satellite. I'm not sure anybody else does yet, but it's possible the US has one and it didn't announce it, something like that. But it's an option, and it's a serious one that people are thinking about. Now, there's a way to upgrade this a little bit so you don't have to trust the satellite, which is to have the satellite beam down entangled pairs to both Alice and Bob. And that does kind of have a distance limitation, but it's much, much bigger, right? It's just, instead of being 200 kilometers from each other, Alice and Bob have to, at some point, be 200 kilometers from the satellite. It's actually less than that because the satellites are in low Earth orbit, is not that high. And the problem is that the satellite can't necessarily keep this entangled pair living for very long. So they both have to be in view of the satellite within a relatively short time period. But you can certainly get much longer distances than you can with optical fibers that way. And so that's one option. But the real long-term option is to build a network of something called quantum repeaters. So classically, we have optical fiber networks all over. And of course, we have the same problem of loss, that you send photons into optical fiber, and they get absorbed or scattered out. And over long distances, you'll lose signal. And the solution to that is to have little boxes that occasionally will measure the state in the optical fiber and then inject some additional light to duplicate what was there. Okay? Which is fine for classical communications. But from the point of view of QKD, that little box looks exactly like an eavesdropper. Right? It's measuring the state and it's resending. So that's not what you want to happen. What you can do instead is have those little boxes doing quantum error correction. Right? And that can compensate. You can have error correcting codes that correct for loss of photons and for other kinds of errors. And so in principle, if you have these little error correction boxes everywhere, you can send QKD for arbitrarily long distances. It's worth noting that we don't rely on these error correction boxes being secure from Eve. Eve could break into them and change them, but one of two things would happen. Either the error correction boxes don't correct errors anymore, in which case we're going to end up, Alice and Bob are going to abort the protocol because the error rate will be too high. Or the quantum repeaters do correct errors, and in that case, the quantum state that Bob is receiving is the quantum state that Alice sent, and this whole security proof applies. Okay? Yeah, so the actual way you would do it is not using quantum error correction. Instead, you'd use something called entanglement distillation. So Alice and Bob are again going to try to get entangled pairs. So each repeater is generating an entangled pair. It goes for a short distance. Then you connect up multiple repeaters using entanglement swapping, which you did in one of the earlier tutorials. And so then once you've done that entanglement swapping, Alice and Bob have an EPR pair over arbitrarily long distance. And then you can do the stuff I was mentioning before. OK? So the bottom line, though, is that in order to make this long distance, you need this kind of slightly more advanced quantum technology, which is not as big as a big quantum computer, but also requires an interface with communications. And so the progress in that, I think I mentioned, has been a little bit slower than it has been for quantum computers. So the quantum repeaters, I think they've been demonstrated. But again, it's something that's not commercially viable at this point. OK? OK, so are there questions about that? OK, then that's it for today. Tomorrow, I'll be talking, I think, about quantum compression and some kind of information theoretic properties. And then Friday about entanglement. So we're going to the properties of quantum states directly.